So the event we're going to talk about is the Balkan flooding in November 2016. And we're going to focus really on how well did the EFAS perform, how did the EFAS forecast look, and really focus on the products that are available within the EFAS IS, so that you can see how we as forecasters would work. The reason we chose this event was because it was the most recent relatively large-scale flooding event where all the latest EFAS products were available to us as the EFAS dissemination centres for the forecasters. It was really a series of events that covered most of the Balkan region in November 2016. And both Albania, Kosovo, Montenegro and Serbia were most severely impacted. Most of the impacts were actually in Albania. And then there were also further impacts towards the north in Bosnia-Herzegovina and in Croatia. In Albania there were 3 fatalities, 80 evacuations. There was widespread support from military and rescue services across 6 different counties. One of the main highways were closed, there were numerous landslides and bridge collapses, and there was extensive flooding in agricultural areas. Similarly in Kosovo there were 1,000 families affected, water supply and power networks were affected. Montenegro, nearly 400 evacuations, impacts across 3 different counties, and similarly in Serbia, 40 evacuations and damage to a number of houses. I'll allow our Croatian colleagues to talk about the impacts that occurred in Croatia. But as I said, most of the most severe impacts were towards the south in Albania, and that's where there were fatalities from the event. Very briefly on the rainfall accumulations. So this event, the rainfall that fell over quite a long period of time, nearly up to a week, and we'll show the forecast a little bit later and how they looked. But the rainfall totals, and this is taken from the ECMWF, this is an interpolated gauge product, so this is observations. There's 2 different figures that you're looking at here. On the left side, the table shows you how much rainfall fell between the 6th and 12th of November in Montenegro. So over a 6-day period, 7-day period, you can see that there was more than 400 millimeters in certain places. But I think the important point is that widespread there was more than 100 millimeters over all the different catchments. So it's significant rainfall totals. The map is showing you the totals that fell over a 48-hour period between the 7th and the 9th of November. And there's these 3 quite obvious regions that had most rainfall, both in Albania and the border to Greece, and then in the north with the border to Montenegro, and also in the north of Kosovo on the border to Serbia in that region. And there it was up to 150 millimeters in a 24-hour period. So basically there was a lot of rainfall and there were really 3 different rainfall events that occurred.
We're going to head on to the notifications that are issued in EFAS very, very briefly, because we know that most of you already know this. And this is Simon, by the way, at SMHI, sitting next to Richard. So we'll briefly go through here the formal notification. We'll start with that one, that the officers on duty issue once they see something in EFAS. And they issue it for catchment areas that are larger than 2,000 square kilometers if the event, the forecasted event is more than 48 hours in advance, and if the forecasts are persistent. If there are 3 consecutive VAREPs or cosmolets forecast with more than 30% of the ensemble members exceeding the threshold, which for now is 5-year return period of the discharge. Also, at least one of the deterministic forecasts need to exceed this threshold, 5-year return period. To issue an informal notification, the second one, that can be issued if any of the above criteria is not met. That means if the forecast persistent isn't that good, or the lead time is less than 48 hours in advance, or if the catchment size is smaller than 2,000 square kilometers. But officers on duty wants to stress that the situation is could be extreme, for example. The last notification that we issue is the EFAS flash flood notification, and this is based on this is not a fluvial notification, it's based on runoff, which is calculated using the ERIC index, the enhanced runoff index based on climatology. And we talked about that one on the last webinar we had a couple of months ago, so we won't go through that much. Also here, the forecast, the ensemble members, more than 35% of the ensemble members needs to be above this 20-year return period threshold, and the event must be within 72 hours. And during this event, the officers on duty issued 7 formal notifications for Albania, Greece, Montenegro, and Serbia, 7 informal notifications for Albania, Croatia, Greece, Macedonia, and Serbia, and 33 different flash flood notifications for a wider area. This is a timescale that we created to show you, giving you more or less a better understanding of the event. So on this timescale, we start at the 31st of October and we finish at the 12th of November. At the 31st of October, we see the first possibility of flooding in EFAS. So on this day, we'll go into the EFAS system and take a look at what EFAS perceived at the time. Then we'll jump into the system another time on the 1st of November, when the officer on duty issued the first formal flood notification for this event for the Moracha River in Albania and Montenegro. Then we'll jump in time and go to the 4th of November, where the first flash flood notification was issued for Croatia. And then the last time we'll go into the interface is on the 8th of November, where the event is at its peak, you can say. So on this time scale, you see all issued formal notifications in red, all issued informal flood notifications in orange, and all issued flash flood notifications in gray. And the flash flood notifications, we're only writing the name here of each country, because in some places there are several flash flood notifications issued at the same time for the same country. So make the timescale a little bit easier to read, we exclude this information. And under the timescale, you see some arrows indicating the date when the notification was issued, and ending by the end here of the arrow where the threshold of the 5-year return period is exceeded. And we show this for all formal and informal flood notifications. And you can see here on the time scale that the lead time is quite long for most of the time, around a week for some notifications, and then the closer we come to the event, the shorter the lead time is. Also, for the flash flood notifications, we don't show any specific lead time because it would be impossible to show all these 33 here on this map. Yeah, but all of them have a lead time not more than 72 hours, 2 to 3 days most of the time. So we'll start here and go into EFAS on the 31st of October. Let's see, where do we have it? Here we are. Okay, so now we are on the 31st of October, and we look at yesterday's model run. You can see it here in the Select Layers tab. We are at 2016, the 30th of October. That's the model run, but you are in real life, you are on the 31st of October. So what I want to show you here is some other meteorological models. Actually, Callum, you have already shown us quite a lot of meteorological information, but we just want to show you here some projects you can look at in EFAS to detect an event such as this. So we won't show you any impacts or information such as that here. We want to show you how officers on duty work and some useful EFAS products. And we'll start here with the accumulated precipitation, the deterministic model coming in from ECMWF. And we can show you information about these models here. We have several meteorological models in EFAS, but during this specific case study, we'll only show you the deterministic ECMWF model and the ensemble one, since the forecasting days are they're up to 10 forecasting days for this model, while the DWD one is only 7 days. So we'll take a look at the ECMWF one. We'll zoom in to the area of interest, and we see here that in the forecasting range, the 10 days, we have quite a lot of precipitation coming in. Very high intensity and localized precipitation coming in here, up to 140 millimeters. We'll also take a look at the animation here to give a more detailed picture about the event. You can press the play button here to see what happens at each time step, and the resolution is 3 hours. So the rain will come in here a little bit later on, Wednesday, Thursday. The first rain comes into the area, and then it continues during the weekend, Saturday, Sunday, Monday, and Tuesday. So there are several bands. Exactly. Thank you, Richard, coming in. We'll go into the reporting point, which is seen here. This is the first hydrological signal that alerts the officer on duty, for example. If you click on this reporting point, a window will pop up showing us the geographical area, some information about the upstream area, and also a discharge hydrograph showing us all different, the list flood model that has been run with several different meteorological models, which we've already discussed. And here we see that the some ensemble members goes up here towards the end of the week, probably because of the incoming precipitation. But for the DWD model, which is only 7 days, we don't see any signal because it ends before the precipitation comes in. And you see that the peak is on the 7th, and that some of the ensemble members goes above the return period of 5 years, which is the threshold for notifications. Yeah, and you also see in this graph this dotted line here, which is the maximum simulated value from the historical period that has been simulated with the list flood. Yeah, it's only modeled. So here you can compare that with the historical simulated discharge with the upcoming one and see if how worse it can be, or how bad it can be. Then we'll scroll down and show you some of the upstream rainfall that can come in here. And as you see, the date is not really the same here. Here we start at the Sunday, the 30th of October, which is here. So this only shows the forecasting period, while the discharge hydrographs shows historical period as well. So we see that some different models give some different precipitation coming in here for the coming week.
Can I say one thing? Yeah. I'll just say one thing as well here on the discharge hydrograph. These black marks that you can see here on the first one, they are when the model has been run with observed rainfall and other variable temperature, whatever the model needs. So this is what the model thinks would have happened based on the best possible in data. So it's not observations, it's not gauge observations, but it's the model that's been run with observed rainfall. So that you
Yes, thank you, Richard. Now we'll go back to the timescale. So we were at the 31st of October. We'll jump one day ahead to the 1st of November to see. We'll go one day ahead here. Take a look at the run on the 1st of November. Because this day, the first formal flood notification for the event was issued here in Albania and Montenegro for the Moracha River. We'll zoom in to understand why it was issued. We click the reporting point button and we'll skip the information here. You can just look and see that, all right, it seems that we're going to exceed the thresholds. But we'll take a look at a table in the lower end here. In this ECMWF ensemble table, you can see the percentage. These numbers depicts the percentage of each of the ensemble members that goes above the 5-year return period threshold. And the horizontal digits here shows the dates. So here we are at 6 and 7 of November. And here's all the model runs. So to issue a formal flood notification, we need more than 30% of the ensemble members to be above the threshold, and we need 3 consecutive runs. So here on the 1st of November, we have 3 consecutive runs above where the model ensembles are above 30%, 35, 61, 59. So it's quite clear that something is going to happen here, according to the model at least. And you can also see that quite a large amount of the ensemble members are reaching up to the 20-year return period even. So today, a formal flood notification was issued for Moracha River. We'll go back to the timescale. And we'll jump a couple of days ahead here, because next day we have another formal flood notification issued for Greece, another 2 formal flood notifications issued for Albania, and another one for Greece. And we'll jump back into EFAS IS on the 4th of November to take a look at the first flash flood notification. Please bear with me. There we go. Now we'll zoom out. Yeah, we'll uncheck some layers as well to make it easier to see what we're looking at. Now we're going to move north to Croatia, where the first flash flood notification has been issued. And this purple colored area, as you see here, is a drainage area where we have a lot of runoff that exceeds the 20-year return period runoff. And at the bottom, or in the lowest point in this area, we have a triangle giving us some possibility to click on it, the reporting point. And it shows us a graph quite similar to the discharge hydrograph, but it's calculated in another way. But it's more or less the same thing here. We have this is not the ECMWF model, for example. This is based on the Cosmolabs run, which has 16 ensemble members. And to issue a formal flash flood notification, we need 35% of the ensemble members to reach this 20-year return period threshold. And in this case, we have 43% of them reaching the 20-year return period threshold. And we are on the 4th of November, and we see this signal more like 2 to 3 days ahead. So a flash flood notification was sent. And if you want to know more about flash flood, you can watch the second webinar that we had a couple of months ago. Yes, and another thing that is interesting here in this for these flash floods is the landslide susceptibility of the affected area. So you can take a look here at very high, high, and moderate landslide susceptibility for this specific area. And this is based on a static map, which in turn is, I'll just have to close some of these things, which is based on topography and soil type. And this map is accessible both in EFAS, and if you want more information, you can click on this link here that's shown in the legend. And you can see that in this area, the susceptibility to landslide is quite high. And that's about it for me. I'll hand over the microphone to Richard. So please wait a couple of seconds.
Okay. Hello again. I will not take much more of your time before we look at the Croatian example. So if we just go back to the timescale of the event, now going to jump into when the event really occurred, which was the 8th and the 9th in most regions. I should say that in Croatia, the flash flooding occurred a little bit earlier on, but again, I'll leave that to our Croatian colleagues to discuss. I want to focus on 3 specific things rather than I don't want to go through each of the specific warnings or notifications that were issued or look at specific rivers, because you can do that yourselves by going back through the event in your own time. What I do want to do is look at 3 other products that are very useful when you're trying to understand how an event might occur. So if we go back to the interface, I will now turn off landslide susceptibility, and again, please bear with me whilst everything loads. And I'm just going to zoom out to the whole area and just have a look at how the forecast progressed before looking at 3 specific products. So if I turn on, we have that already. And we have EFAS active information. What you're really going to see is that once it loads, it's a bit slow today. Now it's loaded. What you're really going to see is that the notifications that were issued, as Simon has already said, they're quite consistent. They're out for quite a long time with quite long lead times for this particular event. So now I'll just click through basically, and you'll see a lot more flash flood notifications get issued in this southern region as we progress through time. So now we're on the 5th, 2 runs on the 5th. You can really see how this event spreads inland towards Serbia, Kosovo. And now all of these points here with the little thunderstorm symbol, which symbolizes the flash flooding, you can see there's quite a large risk of flash flooding across the whole area. And if I continue through to the peak of the event, now we're on the 7th, and now we're on, next click, we're on the 8th. So this is really when the event was at its worst. You can see a very considerable area was affected. Now we're mostly focusing down in the southern region, not so much in Croatia. Croatia came earlier in the week. And what I do want to look at, rather than looking at specific points, because there are so many to look at, and what I want to really show is 3 specific products within EFAS IS, which are very, very useful when you're trying to understand an event. The first one I'll start with is the soil moisture information. So now I will turn off the EFAS active information, and I will turn off the flash flood points because they are a little bit hard to see through. So if I go into hydrological layers, nope, that was wrong. If I go into initial condition layers, so these are the layers that go into the model. So when the list model is run, these are some of the layers that are required in order to run the model. But if we focus on soil moisture, and there are 3 different ones here: the soil moisture, satellite soil moisture, and soil moisture anomaly. Soil moisture is as the model was calculated. So this is as comes out of the model. And it basically goes from 0, red, up to 1, where 1 is most wet. So at 1, basically the soil layers in the model are saturated. That one is less useful, I think. And satellite soil moisture is the same thing, but from observations. So again, 0 to 1. But the one that is very useful and that gives you some context is soil moisture anomaly, the third one here. So soil moisture anomaly is calculated as an index, where the index goes from red, highly drier than normal, up to blue, highly wetter than normal. And this is again based on the list simulation, so this is based on the model, but it's calculated as how it deviates from the normal conditions based on this 22-year climatology, so 1991 to 2012. And what we can see in this event, if I now turn back on the flash flood notifications, or the reporting points in any case, there is in some areas you can see that generally we have quite a large surplus of water, of soil moisture. So between wetter and much wetter, and in certain areas highly wetter than usual. And that is one of the reasons that we saw this large-scale flash flood response in combination with the rainfall, the large rainfall accumulation. So it was the effects of both of those that led to the flooding down here, anyway, in the southern regions. That's one product I want to focus on. The other one, which isn't directly related to the event, but it's very useful for a forecaster, is how good or not good the model is. So again, I will turn off the reporting points. In fact, I will now turn off everything, so it's very clear. I'm going to look at hydrological layers, hydrological validation. Hydrological validation is a summary of how good or bad the model is based on the Nash subcliffe efficiency, NSE. I imagine most of you are familiar with that, but for those who aren't, anything less than 0 means that the model has no skill. Anything more than 0 means that the model has skill. So here we can see, for example, if I take this point in Serbia, it's got a green value. Tool has a green value, which means it's greater than 0.5. And here we get some very useful information up. We only get this information where there are observations. But here you can see, based on the calibration period, which is 1995 to 2002, we see the observations in black, and we can see the model in blue. And then if I scroll down, you can see the NSE value down here, NSE 0.54. So the model has some skill here. We would hope it would be more like 0.7 in general as a rule of thumb for a good model. But 0.5 means there is a lot of value in the model. But something you can see, and it's very important, is that the model here, the blue line, usually underestimates the peaks. And we can see that in the graph down here as well. I won't go through the graph, but you can see that there's more extreme values in this graph than compared to the observations. But just looking at this time series, generally the observations are much more peaky than the model, which means the model is missing the highest runoff values. But actually in EFAS, because all the EFAS calculations are based on return periods, so we're comparing the model forecast with the simulated model, that means that it's all relative, basically. So if the model on average underestimates compared with the model values, then the return period is still relevant, even though compared to the observations, perhaps we underestimate. And it says that down here when you click on the little information thing here. Note that in EFAS, the systematic under or overestimations are compensated by the threat of exceedance approach with forecasts. So because we're comparing model with model when we look at return periods, we kind of get around this problem. So there is still value in EFAS forecasts, even where the model has not good performance. And that's very useful actually in this region where there's not so many observations, because it means that we can still say that the model is very useful, even though we can't validate the model. The last thing, very, very quickly, before I hand over to Tiana in Croatia, is a new or relatively new product, is the seasonal outlook. Unfortunately, this product only became available in November 2016, so just before the event started. If I zoom out to the whole of Europe, yes, so yeah. So the colors here, this is a seasonal outlook. So this is based on running the list for simulation over an 8-week period and then aggregating the results of weekly values. And basically it's telling us where it's blue, it's telling us that there's a high probability of high flows, where it's red, there's a high probability of low flows. And this is run once a week, this particular simulation, and updated once a week. But like I said, this only became available in November, so 1 week before this particular event occurred. But again, you can see here, it's very good because even, okay, it's only a week before, we would hope to see it several weeks before, but we can see a week before a very strong signal for high flows across the whole of the Balkan region. And if I click on this this area, I then get a graph which tells me for each of these 8 weeks what the model expects the flows to look like based on the whole region. So it's the average across the whole region. And basically, when I go above this blue line, I'm above the 90th percentile. The numbers at the top tell me how many of the runs are above the 90th percentile. For example, for this event, which based on this run, which is the beginning of November, and the event occurred in week 2, then 96% of all models are above the 90th percentile. So there's a very, very clear signal that there are going to be high flows in this region. This isn't a tool that we use currently in terms of issuing notifications, but it is something that we have begun to look at to give us an idea of what kind of event might be occurring over the next 2-month period. But it's something we hope to use more in the future.